Okay, well, this is our final lecture of the semester, so we'll jump right into it. Just so you know, I did finish the final exam, so I will be posting that sometime after we get through with the lecture today. And I'll have, towards the end of the class, I'll have some instructions on how you could submit that final exam. So let me jump right into the material. We were talking about magnetism, and we talked about a couple things. Number one, there's two sources of magnetism that we want to consider. The first source we started in the last class, that was magnetism caused by a permanent magnet. And today I want to finish that discussion, and then I'm going to talk about electromagnetism, which is magnetism that we can control. And so we showed this example of a bar magnet. In the last class, we mentioned that bar magnets have poles, north and south poles. And that like charge, the law of charge, that like charges repel, unlike charges attract. Poles act the same way. If I have two like poles, two norths or two souths, they repel each other. When I have unlike poles come together, they attract each other. So just like forces, electrical forces, magnetic forces kind of behave the same way. We also talked about that these lines of flux or force, is what the term we use, exist around any magnet. And I kind of do it like this. I do these lines coming out of the North Pole and going into the South Pole. And so I drew a few of these, and we mentioned the fact that this represents the field, the invisible field that exists around any and all magnets. And we started to talk about some vocabulary. These lines right here represent lines of force. We gave them the name flux. And the group of flux represents what you might call the magnetic field. We also talked about the origin of all magnetic fields. And we spent a lot of time in the last class discussing that, or talking about the fact that magnetic fields are created by current. Electric fields are created by charge and motion. We talked about how fields are created inside of the bar magnet. We talked about the domains, the magnetic domains, which represent the magnetic properties of atoms, and the fact that in a permanent magnet, all those domains line up. So we get a net north and a net south pole. And then other materials like this marker or any other thing that doesn't have magnetic properties, those domains cancel out. So it's important that you look at that last video if you didn't have a chance to do that in order for this one to make sense. So please go back and review that. When we talk about flux, there's a symbol that we use to represent flux. You use either that one or that one. And then I think I mentioned the fact that there's units. Flux has units. So these represent lines of force. So one line, we give it the unit of Maxwell. So one line equals one Maxwell. And we mentioned in the last class that this is a CGS unit. And I can have a group of lines, and we use the Weber as the unit. And so this right here, the Weber, is the MKS unit. And so if I want to talk about small or relatively weak magnetic fields, I use Maxwell's. If there's something bigger or stronger, I could use Weber's. So the way to abbreviate that is, if I'm using Weber's, abbreviate it WB. If I use Maxwell's, I abbreviate it MX. And so right here I have 1, 2, 3, 4, 5, 6 lines of flux. So I would say I have 6 MX or 6 Maxwell's for flux. And so we mentioned that. Now, one thing you want to be able to do is to go from the CGS unit to the MKS unit. That is to go from Maxwell's to Weber's. And so there's a relationship for flux that relates Maxwell's and Weber's, and that relationship is that 1 Weber equals 1 times 10 to the 8th lines are 1 times 10 to the 8th Maxwell's. So you want to remember that. Now, if you were in lab, there were some handouts. I passed out a couple handouts. I'll post those handouts today. By the way, I will post them. If you didn't get a chance to come to the lab, I know a couple people missed. But there was a handout. There was the final homework. I passed that out. And on that final homework for capacitors, you're supposed to do problems 1, 2, 3, 4, and 5. There was a topic sheet for today on magnetism. But then there was this other paper where it had some practice problems that we're going to try to get through today. And if you take that out and you look at problem number 1, I'd like for you to go ahead and work problem number 1. It's just a simple conversion using this relationship. We're going to convert Maxwell's to Weber units. So in case you don't have the paper, I'll read it. You have a magnet, produces 40,000 Maxwell's of magnetic flux. Now notice, I just have 6 lines here. I think I mentioned in the last class, you'll never have a magnet with so few lines of flux. You'll have literally hundreds of thousands or even millions of lines of flux. So this is just an example here. This is more like what you would actually find in the real world. You have 40,000 lines, 40,000 Maxwell's. So we have 40,000 Maxwell's of magnetic flux, and we want to convert that to Weber. So see if you can go ahead and do that, and then we will look at it together. My flux is 40,000 Maxwell's, and I want to convert that to Weber's using this relationship. And so we set that up while you guys are working. I have, I'll just do it in scientific notation so it'll be easier. So phi is going to be, this is 4 times 10 to the 1, 2, 3, 4. 4 times 10 to the 4th Maxwell's. Question?
0.4 milliwebers.
Is that what you got?
I think.
Okay, well, let's just see. So we have, using this, 1 times 10 to the 8th Maxwell's is the same as a Weber. I like to set them up like this. This is if you had a chemistry course, it's probably your chemistry equation. You set them up kind of like this, and the units kind of cancel out nicely. So using this conversion factor, I think it was Ben that said he got an answer, but we'll just check it out and see how close that is. If I take divide that, I get 4 times, and divide that, I got times 10 to the 4. I bring that up, it'll be times 10 to the minus 8. So that'll give me 4 times 10 to the minus 4. We're in Weber units. I don't know if I'm out of, I think I'm out of the board here. Let me move that over. I think I'm out of the range of the camera. I came in this morning, and when I turned the computer back on, it started to update, and I had to wait for that after it cut out on me. And then somebody had moved all my equipment. I told you somebody comes in here, every time I leave out of here, there's something moved or something adjusted. So anyway, it only happens when you're in a hurry. So we got, what was it, 10 minus 4, and my units would be Weber's. So you can leave it like that, or if you want to convert it to milliwebers, then I think that was Ben. If I move it over one place, it would be 0.4 milliwebers. So either way, it's okay for me. I don't think that's a big issue. You guys, exam is a take-home exam, so if I ask that question, surely nobody will miss that if that question is asked. So, Now, I want to talk about another quantity that's actually kind of important, more important than flux, because when you deal with permanent magnets, usually what you're concerned about is the magnetic field. And you might think, all right, well, then we just talk about the magnetic field. Well, when we think about the magnetic field, we actually think about this. There's this term called flux density. Flux density. And when we talk about magnetic field, that's actually what we refer to. That we're referring to the flux density. So when you talk about density, well, what is density? You have a certain amount of space, and it's how condensed things are in that amount of space. So the more dense things are, the more things are grouped together in a certain volume or space or mass. So this idea of flux density is equal to the amount of flux per unit area. The amount of flux per unit area. Now, for flux density, they use this symbol. They use a symbol or the letter B. I don't know why they use a B, but they use a B for flux density. Of course, for flux, they use, I don't know, Ben, you said it was phi or phi. They use this. And then for area, of course, they use A. So imagine that you have a unit area, like this, the area of this paper. You have area. And then what you do is you're going to count how many lines of flux cut through this area. So I can see right here, I got 1, 2, 3, 3 lines of flux cutting through that area. If I move it up here towards the pole, either the North Pole or South Pole, I have way more flux per unit area than I have right here. So the magnetic field will be stronger at the poles than it is over here, because the flux density is higher at the poles than it is over here off to the side. So when you talk about magnetic field, you're really not talking about the flux by itself. What you're considering when you talk about the strength of a magnetic field, hey, this magnet has a really strong magnetic field, you're talking about this, you're talking about flux density. And so this turns out to be the most important quantity.
You also start taking distance away from the magnet to work with flux density as well, or is that not part of that equation?
That's not part of this equation.
Okay.
Just the number of flux lines per unit area. Now, if you think about this, let's say that I measure this right here in Maxwell's. Now remember, a Maxwell is a CGS unit. So if this is in Maxwell's, then CGS, then my length is in centimeters. So if I think about an area, 1 centimeter this way and 1 centimeter up and down, and this is a square centimeter. So the area would be here in square centimeters. If I consider flux density, and instead of using Maxwell's for this, let's say I use the MKS unit of Webers. So here I have Webers, and Weber, that's an MKS unit. So then this area down here would be in meters squared. So you want to remember that if my flux density uses Maxwell's, then when you do the division, you got to divide by square centimeters. If my flux density uses flux in Webers, then you got to divide by square centimeters. Now, if you remember when we talked about current? When we talked about current or voltage, some of those were derived units. For example, if we have a joule per second, that's how we measure current in joules per second. But we define this to be 1 amp. Or when we talked about voltage, we have a joule per coulomb. When we talked about that, we define this to be 1 volt. Well, just like we have this derived unit here, what we do is, for this one, for Maxwell's, if I have a Maxwell per centimeter square, one of those, that's equal to 1 Gauss. So if you're using, you can use this if you want to, Maxwell's per centimeter square, but they refer to that as a Gauss. And the way they write that is a capital G. So Gauss would be the CGS unit for flux density. Well, what about this one? What if I use Webers per meter squared? Now this one you'll be familiar with. If you use Webers per meter squared, then we refer to that as 1 Tesla. And so you guys, some of you are familiar with Nikola Tesla. He has a unit of magnetism named after him. And the unit, the way you would write that is a capital T. Normally, I won't say normally, at least for me, I usually tend to work with MKS. Every once in a while, we'll jump to this one. You should be able to easily handle either one. But I think most of the time, you'll see, because most of the time you're dealing with magnets like maybe if you work on if you have to do some work on an MRI machine, it has a really strong magnetic field, it would be in Tesla. Or the magnets that they use in computer hard drives, really strong magnets, would be in Teslas. But if you were doing some work, it's like a really weak magnetic field might be the magnetic field around the Earth, extremely weak magnetic field. You probably would measure that in Gauss. But again, you should be able to use either one of these units. Okay, so just fix that kind of in your mind. No flux. These lines right here, lines of force. But when we refer to magnetic field, we're really referring to flux density. Tesla, Gauss are units for flux density. Okay, any questions over flux density? Because I think we have, yeah, we got a simple conversion problem. So anybody have any questions over what we mean by flux density? I think it's pretty straightforward. So if you have the handout, take it out. If you don't, I'll read it. And again, I'll post this so that you have it for your notebook. If you're keeping the class 3-ring binder, you can put this in your notebook. So I'll read this. It says, with a flux density of 25 microwebers through an area of 0.04 meters squared, what is the flux density in Tesla units? What is the flux density in Tesla units? So you have this magnet, and they give you the flux that the magnet produces. They say that flux is 25 microwebers. 25 microwebers. And they tell you the area that the flux cuts through is 0.04 meters squared. They want to know the flux density, and they want that to be given in Tesla. So what is that value right there? So go ahead and get your calculator out. Did somebody's hand come up, or was that something else? Go ahead and calculate that for me. Okay. So if I put my numbers in there, flux density. And by the way, for those of you who are, you have a background using vectors, if you know what, if you don't know, don't worry about it. It's not a big deal because we're really just dealing with magnitudes here. But flux density is actually a vector, it has a direction. Flux density has a direction. So if you have an area, well, I don't want to go into that. I'll get off on a tangent, but just know it's a vector quantity. If you deal with vectors, that might be of interest to you. If not, just forget that I even brought it up. So flux density would be the flux per unit area, and this would be 25 times 10 to the minus, this is minus 6 Webers. divided by 0.04 meters squared. This is already in the right unit. It's already in square, but if that had been in something else, like centimeters, you'd have to convert that to meters squared. So somebody on your calculator, divide 25 by 0.04 and let me know what you get. 25 by 0.04 is what?
625.
645?
25.
645 like this. Your microphone's muffled.
625.
625. So is that just 25 divided by 0.04? So this is 625 times 10 to the minus 6 Weber meters squared. And so I would change that to Teslas. So, and I don't really have a feel for how strong that is. I mean, I don't really didn't do a whole lot with magnetism other than the number thing. So, but there you go. So that's pretty simple to do. So that's it with permanent magnets. Anybody have any questions on permanent magnetism? I will mention one thing, and again, I don't want to get off on a tangent, but a long time ago, one medium they used to record music, they used to record computer data and other things was, if you know what cassette tape is, or maybe an 8-track tape, they use a tape with a metallic material on it, and they can actually record the magnetic dipoles. And as you'll learn here in a few minutes, that if I have magnetism and I cause that magnetism to move, I can create electricity. So without going into the details of that, you can use this idea of these little magnetic dipoles to actually store information. And a few decades ago, that's the way they used to store information for computers. And that's the way I remember as a child. This was before where they have MP3 players now. Before that, it was a while back, they had cassette tapes. And when I came up in high school, we had cassette tapes, and we have our music and our information stored on cassette tapes, and that's based on those magnetic dipoles and principles of magnetic dipoles. So let me get into what I really want to get to, and that's electromagnetism. That's really important. This is important, but electromagnetism is really important because electromagnetism is magnetism that we can control. So I want to talk about that. So go back to our discussion from last class, and I mentioned to you that all magnetic fields, the origin of all magnetic fields is charge and motion. And so we talked about the charge and motion around an individual atom, the fact that the electron is spinning, and so that spinning electron constitutes a current, and that current, because it's spinning, creates a magnetic field, and at the same time, that electron is revolving, and so that adds additional magnetic flux, and so we can view an atom as a microscopic little tiny bar magnet. Well, here on the macro level, imagine I have a piece of wire. I got a piece of wire. And I put a voltage across this piece of wire. So I got my plus polarity here, and my minus polarity here, and I let current flow through this wire like this. So here's my current flowing in the wire like that. If I have current flowing, then it creates a flux density around the wire, and here's the thing. The flux density is directly proportional to the current that caused it. The flux created around this wire is directly proportional to the current that caused it. The more current I have, the more magnetic flux I have. Now I need to pause for a second and go back to that term that we use, vector. We mentioned in the last class that there's two quantities that you can have in nature, scalars and vectors. A scalar is a quantity that's represented with just a number. So if I talk about the temperature, I think I use the temperature as an example. I don't know, I think it's supposed to be 59 degrees today. That 59 describes the temperature, and the unit might be Fahrenheit, Celsius, or whatever, but you only need that one number and the unit to describe the temperature. Well, some quantities require a number, a direction, and a unit. So some vector quantities would be force. Vector quantity could be velocity, acceleration. These are all quantities that I got to express a size or magnitude and direction. If I have something like temperature or mass, those kind of things just require a number. So without getting too deep into the concepts of vectors, they're really simple to understand on the basic level because we can represent them with just an arrow. So if I want to show something with a certain size and direction, I might do it like that and say, well, that's the vector A. If I want to show a vector that's twice as long, I can just measure this and I can show a vector that's twice as long. So if this was 1 inch, that might be 2 inches. And maybe this represents force. Maybe this represents 10 pounds of force. Then this will be 20 pounds of force in a certain direction. And so with a vector, as long as I don't change the length of it, as long as I don't change the direction of it, I can move it anywhere in the whole universe and it's the same vector. Well, it turns out that magnetic flux density is a vector quantity. It's a vector. And what I want you to think of is this. Think of having that permanent magnet with the flux coming out of it like this. And here's your eyeball. You're looking at this right here. You're looking at that coming out of the North Pole. If you're looking at that, I need a prop here. Hold on a second. Let me see if I got a prop. So you're looking at that line of flux coming toward you, right? And what you're seeing is the point of the pin. Whereas if you were right here, this is your eyeball, you're seeing that line of flux moving away from you. And then what you're doing is looking at the back of the pin. So let me show you another way. Remember when we talked about the magnetic domains, those magnetic domains? The fact that you have a magnet, you have magnetism around an atom because of the pattern of the electrons revolving and spinning. It creates magnetism around the atom, and the net magnetic effect, they call that the magnetic domain. So this little tiny microscopic magnet, they'll represent it like this in a lot of physics or material science books. And this represents the North Pole, and this represents the South Pole. Now, when I do this, I don't have time because I'm writing on the board real fast. I don't have time to draw the diamond and all of that, so I just do it like this. Where the top of that arrow represents the North Pole and the bottom represents the South Pole. So just for a second, I want you to think about this pin as that flux line right there. North at the top, south at the bottom. Let me draw it this way. I got it like this. I got north here, I got south there. So it's like that. Now here's your eyeball. You're looking at this thing. There's your eyeball. If you're looking at that, if I turn it towards you, what you're looking at is the point of the pin. What you see is this. So I want you to think of a circle with a dot in it as a vector coming towards you, something coming towards the camera, towards your screen. Whereas if I move my eyeball over here on the South Pole, down here, that's like being over here. So instead of looking at the tip of the vector, the tip of the pin, you're looking at the back of it. So I can turn it like that. And now you're looking at the back of it. And the way I'm going to show that is like this. Now, why do I need to do this? Well, it's easy for me to show a vector, a quantity with direction and magnitude in the plane of the board. I mean, that's easy. I can just draw it in the plane of the board like this. But how do I show a vector coming towards you, out of the board? Or how do I show a vector coming away from you, into the board? How do I draw that? Well, the way they do it in physics, they use this dot X notation. This represents a vector coming 90 degrees perpendicular to the plane of the board that's coming out towards you. And this represents a vector going into the board. Or think of this represents a north pole coming towards you, and this represents a south pole going away from you. Now, why do I need to do this? Well, again, I'm going to talk about something that if you had physics, you know what I'm talking about. If you didn't, you might not. So it turns out that when you do math with vectors, it's kind of interesting because, and I highly recommend that everybody, even if it's not in your major, take at least one physics course. That's a good thing, a good background to have if you plan on getting your bachelor's degree. Matter of fact, I don't even think you can get your bachelor's in electrical or electrical engineering technology unless you have physics. But sometimes you can multiply a vector times a vector and you get a scalar. A vector times a vector and you get a scalar. And they call that, well, they call it the dot product. Sometimes you multiply a vector times a vector, you get a number. So an example of that is work equals force, which is a vector, times displacement, which is a vector, and you get something called work over here, which is not a vector. Work just has, it's a number, so many joules, not so many joules in a certain direction. But other times you multiply a vector times a vector, and you get another vector. But it's not quite that simple, because let's say I have a vector here and a vector here. So these two vectors, I multiply them together, I'll get another vector that's perpendicular to the plane that these two vectors are in. So it's like that. And again, if you don't understand the math part, that's okay. I don't care, because we're going to really bring it down to where a child could do it. In physics, they call this the cross product. And if you have a vector background, you probably use the cross product. But often, of course, on this level, maybe you didn't have the math or physics where they talked about the cross product and the dot product. So they have something else that we use in place of this to get the proper multiplication, the proper vector using the cross product. It's called the right-hand rule. There's a lot of right-hand rules in engineering, especially electrical engineering. And here's how the right-hand rule works. And again, if you have me for AC, we'll talk about, there's several right-hand rules. But with this one, we're going to figure out the direction of the magnetic flux around this wire. What is the direction of the flux around the wire? So you're going to use your right hand for this. Now, if we're using our right hand because we use conventional current. So that's all I want you guys to think about. But if you ever hear about the left-hand rule and be like, man, that's kind of weird. The left-hand rule, what is that? If the current used is electron flow, they use the left-hand rule. Never ever use electron flow. Big boys and big girls, we use conventional current flow. So for us, it's the right-hand rule. But here's how it works. You take your right hand, your thumb points in the direction that the current is flowing, and again, it's conventional current. The right hand. Now I want you to think of your fingers, but I'm showing one finger, as a vector. So here's a north pole coming towards you. I'm going to draw it like this. And if I'm pointing into the board, the back of my hand, you see a north pole going into the board or a south pole going away from you, I draw it like that. And so here's what you do. To use the right hand rule, on the conductor, your thumb points in the direction of conventional current flow, and your fingers wrap around the conductor like this, with your thumb pointing in the direction of conventional current flow. And you see how my fingertips are at the bottom, and the back of my hand is at the top? I would draw that, fingertips coming out of the board like this, which means the X's are like that. And so you can think of North pole coming out of the board and south pole coming into the board, if you want to think about it in that fashion. Any way you think about it, here's what happens. This conductor actually has magnetic flux around it. Now remember what a conductor is, a wire. A cylinder is like a can of soup. That's a cylinder. All a wire is a really tiny, skinny cylinder that's been stretched and is uniform all the way across. And so the magnetic flux around it actually, if you were to, this is your eyeball. This is your eyeball. So here is my wire. If I turn the wire around like this towards the camera, here's my wire. The flux is coming out on the bottom and going into the top, so it's like this. It's actually rotating around the wire like this. If I turn it toward you, notice my hand, the flux is like this, circulating around like that. Does that make sense? If I reverse the current, look what happens if I reverse the current. If I reverse the current, then my thumb is going this way, and these north poles are at the top, and the south poles are now at the bottom. So I can actually control a couple things. I can control the amount of flux by making the current bigger or smaller. I can control the magnetic polarity by changing the direction of the current. But it gets better than that, because here's what we do. Normally, when we want to use electromagnetism, which is what we're talking about, normally when I want to use that magnetic field around the conductor, it's more efficient to wind that conductor into a coil. Which, imagine this, imagine having a long wire with that weak magnetic field around it. If I put it in a coil and scrunch it down together in a tighter area, then I have a stronger magnetic field. Now here's what's really interesting when you do that. Let me show you the way you draw a coil. Notice this. If I coil it up, I'll have a coil like this. And if I hook this up to, say, a switch and a battery, if I close the switch, then what I get is this. I get flux. And since this is coming out of the top, then this must be the magnetic north. And since this is going into the bottom, this must be the magnetic south. And I'm hoping right now, as you look at this, I'm hoping right now you're thinking, well, hold on a second, Singleton. That looks exactly like the flux that exists around the bar magnet. If you were thinking of that, you would be right, for one exception. We cannot control the flux around the bar magnet. We can control the flux around this coil several different ways. Way number one. What if I put in series with this a rheostat? And remember, a rheostat is a variable resistor. Rheostats, two-terminal device used to control current. So current equals voltage over resistance. And if I have a rheostat, that means I can make this resistance higher or lower. But since the magnetic flux is directly proportional to the current, if I raise the current up, I get more flux. If I lower the current down, I get less flux. So one of the things I can control, by controlling the current through this coil, I can control the strength of the magnetic field. If I want a stronger magnet, turn the current down. If I want a weaker magnet, turn it the other way, get more current, turn it up. Or what happens if I flip my battery over? If I flip my battery over, then from my right-hand rule, you can see that the magnetic polarity is going to change. And now I have north pole down here and south pole at the top. So with this electromagnet, this is an electromagnet. With this electromagnet, I can control the magnetic polarity, the north and south pole, and the strength of the flux density. And so this is used in a lot of applications, guys, a lot of applications. And so let me show you one real quick. And you can just go crazy with this stuff. Really, you can. Let me show you one real quick, though. And there's something else I want to get to. One thing, though, I want to mention that on the coil, often what they'll do when they make an electromagnet, they'll take a metal bar. It's called a core. And they'll wind the magnet, they'll wind the wire around the magnetic bar. And what that does is it makes us feel even stronger. I don't want to get into that. We talk about that in AC, but sometimes you'll see that. But let me show you one application of this. Imagine I have like a tube, like a paper towel tube. Take all the paper towel, you got the cardboard tube. Imagine I have that tube. And I put a coil around it. So I coil wire around it, like that. And I hook it up to a switch in the battery. And then I get a rod. So I got I got a magnet here with a north and a south pole, and I attach that to a rod. Okay, a rod. And sometimes what they'll do is they'll put, it might be a spring here, to keep this pulled down or pushed out. But the point is this: if this is open, I just have a magnet sitting there. You know, it's all supported, so I'm not drawing the support for this. But when I close this, depending on the direction of the flux, if the direction of the flux is so that the flux created by this coil is a north pole and a south pole here, then like poles repel each other, so this rod is going to move up. And it'll stay up until I open the switch. If I reverse the current and I make the north pole here and the south pole here, then that rod's going to be pulled down into the center of the cardboard. And so I can make this thing go up and down. That's called a linear actuator. A linear actuator gives you linear motion, and your power door locks in your car work exactly this way. And I can go on and on and on and on with this stuff, but unfortunately I got like 8 minutes to finish the semester out. So, I mean, there's two things I like to talk about. One is the rail gun is based on this effect, and then something else called motor action, which I won't have time to get into. But these are some interesting things that, you know, you may want to look these up and see how they work, because with what we talked about so far, you could understand it. You should be able to understand how a railgun works, or motor action, how basic motors work, and with what we talked about, you'll understand it. And if anybody has any questions about this after the lecture, I'll be more than happy to go into it. Now, there is one more thing I got to talk about, and I'm probably going to go over a little bit. I got about 5 minutes. I think I can probably do it in 10. And I mentioned to you that if you're taking AC, for me, they're going to, Russ Campbell teaches it in the daytime. If you're taking it from me, this is where, what I'm leaving off with now is where I'm going to pick up in AC. And so I want to talk about Faraday's law, but there's one thing I want to talk about before I get into Faraday's law, because this will help you with a problem on your exam. So I want to talk about Faraday's law. And again, if you have to leave, feel free to leave, but please come back and watch the video. You want to look at Faraday's law, and then what I want to talk about is, before I get into Faraday's law, we talked about capacitors. And I mentioned when we talked about capacitors, there's another device called an inductor. Both of these are energy storage devices. So the thing is, capacitors create an electric field. And we mentioned that electric field is between the plate of the capacitors. Well, inductors are magnetic devices. All an inductor is a coil of wire like this. So it stores energy in the magnetic field. And again, we get into this in the AC more. If you wonder why we don't spend a lot of time talking about inductors, it's because given the choice, most people would use capacitors because we don't like the magnetic fields. The magnetic fields produced by an inductor can cause a problem. So I spend a lot more time talking about capacitors. But for the exam, here's what you need to realize. That remember how you have conductors, capacitors in series and parallel? We mentioned the fact that capacitors in series behave like resistors in parallel. And capacitors in parallel behave like resistors in series. Well, with an inductor, they use the letter L. I don't know why they use an L, but they can't use an I for inductor because we use I for current. But if I have inductors in series, like this, so I have inductor 1 and inductor 2, then they act like resistors. Inductors behave just like resistors. So the total inductance here will be the sum of these. Inductors act or behave exactly like resistors. If I had those inductors in parallel, and again, any formula you could use for resistors, you could use for inductors. So for example, there's a 1 over R rule. Well, I can have a 1 over L rule for inductors. I can say that 1 over LT equals 1 over L1 plus 1 over L2, and I can get the total inductance for that. Or I can use a product over the sum rule. We're going to have R1 times R2 over R1 plus R2. Well, I can just change these to L's if I have 2 inductors, L1, L2 over L1 plus L2. So I think that'll give you the total. So I think on the exam I thought we would have to get to this, but this is pretty simple, so I'm not really too concerned about it. So you need to be able to do that for the final exam. Now, sometimes when they draw the symbol for an inductor, they'll use a coil, and they'll have this double line around it, and all that means is it has a core on it, a metal core. So, I mean, it behaves the same way as just a coil by itself. So you want to be familiar with this formula, and then these formulas for the final exam. I think I threw one inductor question in there because I thought we would get into it a little deeper, but I'm happy. If you can do these equations here, you should be okay. Now, this right here is the start, is the end of DC and the start of AC circuit analysis, Faraday's law. Michael Faraday was a scientist. I believe he lived in the 1700s. Don't quote me on that. I think it was the 1700s. But here's the thing. For a long time, people thought that you have electricity on one side and you have magnetism on the other side. They thought they were two separate phenomena. One day, Faraday was walking. He had a compass, like a compass you use north, east, south, a compass you use to find your direction. You know that's based on it's a little magnet in there floating, and it lines itself up in the magnetic field and always points to the north and south pole. Well, Faraday had this compass, and he was walking, and he walked next to a wire that was carrying electric current, and the needle moved. It deflected. He was like, well, that's weird. He stepped away from the wire and then went back to north, south, where it was supposed to be. And when he went back over to the wire, it deflected again. That was the first time in history that we know of where someone connected electricity and magnetism. Now we know that they're intimately connected. You cannot have a magnetic field without electricity. If you have electricity, it will always produce a magnetic field. You can't separate the two. So they're connected. And Faraday was the one that connected. Now, but he has this law. Now, what is Faraday's law? Well, unfortunately, through Blackboard, I can't show you the video. I'm going to put a video on Blackboard, and the guy's going to demonstrate Faraday's law. He's going to take a coil, and he's going to take a magnet. He's actually going to create electricity. So I'll post that right after this lecture, and I want you guys to watch it. And you'll notice that he took a coil and moved the magnet across it, and it created electricity. Then he'll get another coil with more turns, creates more electricity. He'll get a third coil with like 100 turns. It creates a whole lot of electricity. And so up until right now, the only way you knew to get electricity was from a battery, DC. Well, here's another way to create voltage, which can cause current. We can separate charge using electrochemical reaction, a battery. We can also separate charge using magnetism, electromagnetism. And so Faraday's law is based on that. So in a nutshell, in the video, he'll go into the math of it. I don't do that in this class. I do it in AC. I'll go into the formula. Faraday's law is a formula, but in DC, it's a simple list. Faraday says that you can create or induce electricity if you have a coil as a conductor. It's really a conductor, but we say coil because the conductor is usually coil. If you have magnetic field, and there's got to be relative motion between the coil and the magnetic field. So if I have a coil and I have a magnet, I can move the magnet like this as long as that flux is cutting across the coil, or I can hold the coil, the magnet stationary, and I can move the coil like this. As long as there's relative motion, then what you'll get is voltage induced in that coil, and current can actually flow in the coil if you close the circuit. So we call that V induced. When we create a voltage in that fashion, we say we've induced a voltage in the second coil. And that V induced is equal to the number of turns on the coil times, if you've seen this in math before, delta, you've probably seen delta Y over delta X. That's the change in Y, Y2 minus Y1 over the change in X, X2 minus X1. You've seen this when you talked about slope. Well, anytime in math you want to represent change, you can use that delta sign. And if you know calculus, you use a little d instead of the delta, but that's another topic. So I can write Faraday's law by this N right here represents the number of turns I have on my coil. And then I have this delta phi over delta T. So this thing right here, like that right there would be in, like, say, Webers, and this T would be in seconds. That's Webers per second. Or maybe that's in Maxwell's, and that's in second. It would be Maxwell's per second. Just like I can have coulombs per second, the more coulombs per second I have, the greater my current. Well, the more Webers per second I have, the faster I'm moving that magnet across the coil. And so this right here is Faraday's law mathematically, where the N is the number of turns on the coil, the phi represents the flux of the magnetic field or flux density, and the delta phi over delta T, we use that to represent the motion. And you can see from the equation that V induced is directly related to the number of turns. So if I have a coil and I move the coil in and out through more turns of wire, I get more voltage produced. You can see that V induced is directly related to change in flux. So the more lines of flux I have moving through the coil, the more voltage is produced. Or I can see that V induced is related to this whole thing here, delta V over delta T. The faster I move the coil through the magnet or the magnet across the coil, the more voltage is produced. This is called generator action. And this is why this is a topic of AC, because in AC, we deal with electrical generators, and then in AC, we tell you how this generator actually kind of works. We look at least I look at it on a kind of a molecular level or atomic level, and we see what kind of current and voltage it produces. And that's what AC is about. But this is as far as we go in DC. So you want to be familiar with Faraday's law and know, like you know your address. Faraday's law says that if you have a coil or conductor, if you have a magnetic field and relative motion between the two, you can induce or create a voltage, which can cause a current to flow. And there's a lot of things we can do with this, and unfortunately I don't have time to go into the details of it. But there's one more problem on the handout. Actually, there's two more. So I see I still got a few people there. I'm recording this. I'm just going to go ahead and work this so that the course will be complete, and you guys can be able to do your exam. I don't know if I asked this on the exam or not, but I want to do these two problems, and then that'll be it. So again, if you have to sign off, that's fine. Go ahead and do that. Just make sure you go back before you do the final exam and watch the entire video from today. And make sure you watch that video I made on Tuesday. The video on Tuesday was a capacitor review session. You really want to make sure you watch and understand that video on Tuesday before attempting to do the exam. And by the way, on the exam, I'll say a few words about how to submit the exam after I'm done with this. So just real quick, we'll go through this. I got two more problems I didn't get to. Number 3 says you have a magnetic field. It cuts across a coil having 2,000 turns at a rate of 2,000 microwevers per second. I want you to calculate the induced voltage. So let me write it down, and I'll read it again a little bit more slowly to make sure you understand what's being asked. So it says a magnetic field cuts across a coil having 2,000 turns. So in this equation, the number of turns is represented by the capital N, and there's 2,000 of them. Sometimes I'll put a T there for turns. Sometimes I'll leave it blank. So magnetic field cuts across a coil having 2,000 turns at a rate. Now, anytime you see rate, that means you're going to have a T in the denominator. That's a time rate of change. So rate is the delta phi over delta T. Now, if you're in calculus, if you know calculus, it'll be d phi dt. So if you know calculus, you know what I'm talking about. If you don't know calculus, ignore it. Just come over here and do that one. So the rate of change is 2,000, and the unit would be microwevers per second. And so what you want to do is stick that over into this equation and see how much voltage is produced in Faraday's law. Oop, why am I erasing that? So if you have a calculator, go ahead and take that out. And I don't know if I'm out of the frame of the camera here. Let me move this over. So my V induced is going to be the number of turns, which is 2,000. I'm going to put this in scientific notation. 2 times 10 to the third times 2,000 times 10 to the minus 6 Webers per second. So if I do the math here on this, I'll multiply that times that. That's going to give me 4,000. And if I multiply my powers of 10, that times that, it's going to be 4,000 times 10 to the minus third. Now my unit, without going into any kind of deep analysis of the units, my units are going to be volts. So that's going to be volts. So if I write that out, that'll be 4,000 millivolts, or I think 4,000 millivolts. If I move that over, that would be 4 volts. So I can actually create a voltage And you've probably seen this before. Have you ever seen, and I wish I actually have one of these here. Have you ever seen a flashlight? And I'll show this in my AC class. They make flashlights that you can just shake and you can charge it up and then the light's up. Well, what they have is an LED as a light bulb. There's a tube and a magnet and a coil around the tube, and there's capacitors in there. And as you shake it up, you're cutting, and you'll see this in the video when you watch. You'll see the guy actually create electricity. You can actually charge a capacitor by shaking this up. Basically, it's a generator. You charge the capacitor, or maybe you've seen the radio where you crank the radio and you can charge the radio up and you can listen to music. All of that's based on this idea of Faraday's law. We use mechanical motion, electromagnetism to charge a battery or capacitor. I can use that energy to control a flashlight, a radio, or whatever. Oh, wow. It's 10 after, so I got one more problem, guys. I see a couple of you hung in there with me, so I appreciate that. There's one more, number 4. I want to go over that one. I'll give you a second to do it. You can go over it. And then I'll go behind you to see if you got it right. And then I want to mention, so it's on video, how to submit the exam. And then I'll take any questions that you might have. So let me read number 4. And then I'll give you a second to do it. And then we'll do it together. And then we will, now see one thing. Number 4 is written in the calculus notation, but let me explain it here. It says you have a coil of 1,800 turns, and it has an induced voltage of 150 volts. Calculate the flux rate of change, d phi dt, in Webers per second. So let me put that up here. So the 3 things we have in Faraday's law, we got the induced voltage, we got the number of turns, and we got the time rate of change. Well, for this problem, they gave us, they say we have a coil with 1,800 turns. So we got 1,800 turns. We have a rate of change. So now on the example problem, they have what I showed you before, d phi dt. That's the calculus notation for this. Delta phi over delta t, which is the way I wrote this. So if you know calculus, then this shouldn't bother you. If you don't, just change the d phi dt to this, and it'll make sense. Because this is the way you represent change in algebra. In calculus, you use this notation. If you never had calculus before, then this is this one. But so they give us, they say our induced voltage is 150 volts. So in this case, what we want to find is how fast is this flux changing per second. They want to know that in Webers per second. So I'm going to be quiet for a minute and get my calculator while you guys calculate that. And then I'll come back, answer any questions, and then tell you how to submit the exam. Or probably I'll tell you how to submit the exam, and then I'll answer any questions. I'll do it in that order. So see what you can do with that. I'm just going to go ahead and set this up. So we said V induced is equal to N times change in flux per change in time. Okay? Now what I like to do so that this is a little easier to look at, we'll let delta phi over delta t, let that equal x. And if that equals x, and I can rewrite this like this. I can write it as V induced equals NX. And then it's a really, really simple equation to solve if you think about it that way. So, of course, I would just divide both sides by N. And then what I would get is
1 over 12. 1 phi over 12 seconds.
okay, so I get X equals V induced over N, and V induced is 150 volts. N was 1800. I'm just going to leave that as a unitless quantity. This works out a little bit better. And then what we're solving for over here, X was d phi dt, which is what we're looking for. So this is change in flux. I said d phi dt. I'm thinking calculus, but I meant delta phi over delta t. It's all calculus to me, guys. But so this is change in phi over. All right, and Ben, what did you say you got?
1 over 12.
And what? Go. Okay.
So 1 delta phi over 12 delta seconds.
You give me it was 1 divided by 12. Let me divide that out in the decimal.
Oh.
0.083. 0.083. That's repeating. And my units would be, this is in Webers. That would be seconds. So that would be my answer. Whew. All right. Well, I went through a lot there, so good thing we have here's one time I can actually appreciate recording stuff because you guys can still go back, look at it, slow it down and all that stuff. So this is some cool stuff here. I want to see if anybody has any questions, and I know some of you have already left because you had a class at 10 o'clock. So since I'm continuing the class after the normal hours, if you have a question and you're listening to the recorded version of this, you can send me a text today at the number that you normally text me. You can send me a text today, and I'll be happy to, if I'm here at the school, I can come on the board. If not, I'll be happy to respond to your text and see if we can work out any issue or problem you might have if you have a question. Before I take questions, let me mention the final exam. So I'm going to post that here shortly. I'll post that. And it'll be due, my grades are due midnight on Tuesday. So I'm going to have the final exam due Tuesday. I'll let you know the time is going to be kind of early. I want to make sure I have enough time to grade. I wrote it as a test. It shouldn't take you any more than 2 hours to do, probably less. If you follow what we've done here, it'll probably take you more like an hour and a half to do it. It shouldn't take that long. It won't be like exam 3 where you have to spend a lot of time going over stuff. If you understood the concepts for capacitors, again, that video we did on the capacitor review, it'll help you a lot. If you understood the concepts of capacitors and what I talked about today and last time, I think you'll be in good shape. But anyway, on Blackboard, there will be a place to download the exam. I'll put up a copy saved in Microsoft Word, and I'll put up a copy that's a PDF. That way you can have multiple ways to open the document. You will open up the document, you'll download it, and you'll show all your work on the exam. All your work needs to be on the exam. I'll put it like this. Any work you want me to consider needs to be on the exam. Don't just show the answers. You got to show me how you got the answers. The way you're going to submit the exam is if you have a scanner, and your scanner scans as a PDF, and most scanners do, you can just scan the document and you can upload it to Blackboard. There'll be a link. It'll say exam 4 upload here. You'll be able to click that link and you'll be able to upload it to Blackboard directly. So you can download it, you can do your work, make sure you circle your final answers or answer, and you can upload it. You can scan it if you have a scanner. If you do not have a scanner, there are applications that you can there are apps you can put on your cell phone. There's apps you can put on your cell phone that will allow you to take a picture and actually cut the background out, and it'll save that picture as a PDF, and you can upload it that way. And what I'll do is I'll give you, we used that app. There was one particular app that my students really liked back last spring. We went, when we first went virtual, and I'll find the name of it for you. I won't find it right away, but between like now and over the weekend, I'll put the name of that app up. You can use any app. If you don't have a scanner, you can use any app you want to that converts a picture to a PDF. Don't upload the image. Make sure you upload it as a PDF. That way I can make sure I can open it. But again, I will put up the name of the app that we use. I think we use it for several semesters. I can't remember the name of it right now, but I'll put it up as an announcement. And you can use that app or any app. Some of you already have apps that do that. So any way you can convert it to a PDF, you can convert it over, and you can upload it to Blackboard. So the plan is shortly after I'm done with you guys here, I'll upload the final exam, and then I'll make this video also available on YouTube, and you'll submit your homework the same way. That final homework will be submitted the same way. Okay, I think that's it. Now, does anybody have any questions for me? I just saw somebody. Wait a minute, let me go in here. Michael, you have a question?
Yes, Professor. You already answered on that question because I was going to asking you about the homework. So you already did something.
Yeah, that homework, I'm going to have you upload it the same way. Now, guys, it's important, too, that the links that I'm going to provide for the exam, and sometimes what students will do, they'll pass the due date of the time to admit to upload the assignment. That link will disappear. So let's say that homework is due Sunday night at midnight. I'm not saying it is, but if it's due Sunday night at midnight, if you wait till after midnight, you won't be able to upload it. And then what I do, what I get is that students, when the link disappears, and they try to email it to me, and I don't see it in the email, you end up getting a 0. So you want to make sure that you upload your exam and upload your final homework before the due date or by the due date, or else you won't be able to upload it.
So we're not turning it in person anymore?
If you can't. I would prefer it in person. I think that what I said I would do was have you guys, that's a good point. Is that Ben? Who was that? Is that Trevor?
Yeah, it's Trevor.
Yeah. So I had some people that might have been a problem, so I decided to have you guys upload it. Now, I would prefer it in person. I really would prefer it in person. So what I would do is at 10 o'clock, I think I mentioned at 10 o'clock on Tuesday, I'll be here on campus. I'll be here at 10 o'clock. And if you can bring it in person, that would be so much better for me. Only because, well, Blackboard is not too, I'm used to it now because what I got to do is go to the grade book. I got to download. There's a lot of clicking and download it. And then I got to actually grade it online. It's a little easier for me to grade if I have the paper in my hand because I can mark it up rather than grading it on the screen. So, Trevor, yeah, for those people that can bring it in, I would highly appreciate it if you can. I'll be here Tuesday at 10 o'clock. But and that goes for the homework too. If you can bring that in, that would be better. But for those who can't, I will make it uploadable, and you can actually upload it to Blackboard that way. Some people say they couldn't do it.
Personally, Professor, I'm not sending you to Blackboard. I'll come myself.
Okay, I will. Thank you. I appreciate that, Michael. Yeah, that's better for me, guys. But I had a couple students said they didn't know if they would be able to. I don't know what, because the reason I chose Tuesday is because you have that time blocked off. But I think because the semester's over, maybe people schedule some other things to do. So I'll be here Tuesday at 10 o'clock. If you can hand that stuff over, that would be great. If you cannot, you'll have the option of uploading it to Blackboard. Let's see. You guys are talking to each other. Anybody else have questions for me?
So yeah, on homework, do we have to do 3, 4, and 5?
No. Which homework? The last one?
Yeah, that you just get. That you just get.
The one I gave you doing number 1, 2, 3, 4, and 5.
Oh, okay.
The last 3 problems you don't have to do.
Cool.
But the first 5 you want to do. I think one of those has multiple parts, so make sure you answer everything. That'll be an easy 100 points, guys, because I'll probably grade it, I'll be really lenient when I grade it. So you want to make sure you get those points and that you grade it. Okay, anybody else questions? Okay, well, I got people signing off. Okay, I'm going to go ahead and get the exam ready to be uploaded to you guys, and I'll probably put it up there first. I won't provide the link until a little bit later. I want to get it up there, and I got a few other things I want to do today. So I'll put up if you didn't make the last lab, get handouts. I'll put those handouts up on Blackboard, and I'll also put the exam up on Blackboard. So guys, thank you so much. I really enjoy each and every one of you. I hope this semester has been one where you enjoyed it and that you learned something. I know it's a little hard dealing with the circumstances with the virus and all that. A little harder to work virtually, but I mean, I think you guys were a good class, and I think at least most of you applied yourself to the work. So I'm hoping that you came away knowing something that you didn't know before you started, and more importantly, that you had fun while you were learning it. If you're going to take AC next semester at night, I will see you then. There is a little assignment that I may send out early before the semester starts, just so you can kind of get your mind thinking in an AC kind of a way. So if you're taking me for AC, shoot me a text and let me know, and I may give you this little pre-assignment. It's not going to count for any kind of grade, but just some things to think about maybe after Christmas. So guys, have a wonderful, wonderful rest of the year. Stay safe, and if there's anything that I can do for you, even if you're not in my class or classes, anything I can do for you or help you with, please, please, please let me know. Keep my number, and you can text, email, call me anytime, and I'll be available to you. So if there are no more questions, I will see you guys later, maybe on Tuesday if you're going to bring the exam up. If not, I will see you guys around. Thank you so much.